Signals and Systems, Jet Transforms, Part 1, Introduction, Series on Signals and Systems, Lecture number 6.11. Jet transforms are highly useful and widely used in the design of digital filters. These transforms are very much similar to Laplace transforms. Laplace transforms belong to continuous time domain, and Z transforms, however, belong to discrete time domain. In the present session, the focus is on definition of Z transforms along with a few points on its historical development. In addition, we also consider ROC of Z transforms, properties, and common Z transform pairs. Now let us move to the core session. We consider a few points regarding the historical background of Z transforms before going to its actual definition. The Z transform converts a discrete time signal, which is a sequence of real or complex numbers, into a complex frequency domain or Z domain or Z plane representation. Z transform, it converts a sequence, a discrete time signal, from time domain into a complex frequency domain. It is called Z domain or Z plane. As already mentioned, it is discrete time equivalent of Laplace transform. Laplace transform works on continuous time signals, whereas Z transform, it is concerned with discrete time signals or sequences. The basic idea of a Z transform was known to Laplace. It was reintroduced, however, in 1947 by W. Burbidge and others. Later, it was dubbed as Z transform by Ragajini and Jade at Columbia University in 1952. The modified or advanced Z transform, it was developed and popularized by E.I. Jury. See, these are the people who are behind the development of Z transform, who brought the Z transform to a level, to a stage where it is right now. The idea of the Z transform gives a tractable way to solve linear constant quotient difference equations. It is also known as a method of generating functions, introduced by De Moivre as early as 1730. From mathematical point of view, it can be seen as a Laurent series of an analytic function. With this introduction to background, now we move to the actual definition of Z transform. Two types of transforms are there, one-sided and two-sided. One-sided is unilateral transform, two-sided is bilateral transform. Bilateral transform of a sequence x of n, it is usually denoted as x of z. X of z is equal to, by definition, n minus infinity to plus infinity x of n z power minus n. This is bilateral transform. One can define unilateral transform also for a sequence. Definition is the same as bilateral transform except one difference. Here the summation is from 0 to infinity instead of minus infinity to plus infinity. So unilateral transform of a sequence x of n is designated as x of z, and it is equal to sigma n 0 to infinity x of n z power minus n. Inverse transform is one that gives the sequence from z transform. X of n is equal to 1 by 2 by j, closed line integration over c x of z z power n minus 1 dz. Here in the definition we used z. What is z? It is a transform variable, and it is a complex quantity given by r e power j omega. Z power minus 1 over z is delay operator, unit delay operator, whereas z is unit advance operator. Notice the similarity between z and s of Laplace transforms. S is also complex, but S is usually denoted by S plus j omega, but Z is indicated as R e power j omega. The point is, not all sequences can have Z transforms. This is one aspect. Another aspect is transforms do not exist for all values of Z. This is second aspect, second point. Region of convergence is related to the second point. Values of Z for which transform exists. Those values, when plotted on Z plane, they form into a region. That region is called region of convergence. Now a few points regarding region of convergence, or ROC in short, pertaining to Z transforms. The region of convergence, ROC, is a set of points in the complex plane for which Z transform summation converges. This is the definition of ROC. For a given discrete time signal, the following are the possibilities. The Z transform may not exist because of non-existence of ROC. The sequences e power n square, e power n for n more than or equal to 0 are such examples. The Z transform exists but not in closed form. Most randomly generated sequences of infinite length belong to this type. Another possibility is that Z transform exists and can be expressed in closed form but not as rational function of Z. Another possibility is that Z transform exists and is a rational function of Z. These are all possibilities pertaining to Z transform of a sequence. Before closing on ROC, it is to be reminded that ROC is a region over Z plane representing certain Z values for which the transform converges. Now we consider the basic properties of linearity. Here, bare or naked properties are considered. We go deep into them in another session. Let us begin the properties with linearity. Linearity means the transform obeys superposition principle. Mathematical statement pertaining to linearity is transform of a x of n plus b y of n is equal to a x of z plus b y of z. A, b, these are constants. Note, same constants are appearing in frequency domain 2. X of z, y of z are transforms of x of n, y of n sequences. So left side, I can say it is weighted sum of two sequences. Right side, one can say it is weighted sum of transforms of two sequences. So a word statement can be given describing this mathematical statement. The transform of weighted sum of two sequences is sum of same weighted transforms of the individual sequences. Next, time shifting property. In case of unilateral transform or causal signal, transform of x of n minus n naught. This sequence is, its transform is z power minus n naught x plus of z plus sigma 1 to n naught x of minus m z power m. Here n naught is positive. Another part of time shifting property is x of n plus n naught. Its transform can be found as z power n naught x plus of z minus sigma 0 to n naught minus 1 x of n z power minus m. Third property, time reversal. Transform of x of minus n is equal to x of z inverse. Time expansion property. Xk of n, its transform is x of z power k. Another property, scaling property. Alpha power n, x of n, its transform, z transform is equal to x of z by alpha. Another important property, conjugation property. Z transform of x of n conjugate is equal to conjugate of x of z conjugate. Another property, z domain differentiation or frequency differentiation. Transform of the product n x of n, it is equal to minus z d by dz x of z. Transform of n power k x of n, it is equal to minus z d by dz power k x of z. Notice differentiation in frequency domain. It is appearing as multiplication in time domain with n. Here also differentiation k times in frequency domain, multiplication with n power k in time domain. Another property, differencing. Z transform of the difference x of n minus x of n minus 1 is equal to 1 minus z power minus 1 x of z. Next, accumulation property. Z transform of sigma minus infinity to n x of k. It can be shown equal to 1 by 1 minus z power minus 1 x of z. Next, time domain convolution. Convolution property. Here convolution is in time domain. Z transform of convolution between two signals x of n, h of n. It becomes equal to x of z multiplied by h of z. Notice convolution in time domain. It is appearing as multiplication in frequency domain, z domain. Initial and final value theorems. These are similar to initial value theorem, final value theorem that are there in Laplace transforms. In Laplace transforms, these theorems, they are in continuous time domain, whereas here these are discrete time domain versions. When x of n is causal, initial value theorem states that x of 0 is equal to limit z tends to infinity x of z. Final value theorem, it says limit n tends to infinity, x of n is equal to limit z tends to 1, 1 minus z power minus 1 x of z. One can notice lot of similarity between the theorems that are being given here and the theorems that are appeared in Laplace transforms with the same names. Now we consider certain signals and their transforms. Delta function, Kronecker delta of n. For this, Z transform is 1. For u of n, step function, step sequence, Z transform is 1 by 1 minus Z power minus 1. Another step function, minus u of minus n minus 1. For this, Z transform is 1 by 1 minus Z power minus 1. The Z transform of alpha power n u of n. For this, the transform can be found as 1 by 1 minus alpha Z power minus 1. Another sequence, minus alpha power n u of minus n minus 1. For this sequence, Z transform can be found equal to 1 by 1 minus alpha Z power minus 1. Similarly, Z transform of n u of n can be found as equal to Z power minus 1 by 1 minus Z power minus 1 whole square. Some more sequences, signals we consider to give their transforms. Transform of n alpha power n u of n. It can be shown equal to alpha Z power minus 1 by 1 minus alpha Z power minus 1 whole square. Another signal can be considered minus n alpha power n u of minus n minus 1. Its transform can be shown equal to alpha Z power minus 1 by 1 minus alpha Z power minus 1 whole square. The transform of cos omega naught n u of n, it can be shown 1 minus Z power minus 1 cos omega naught by 1 minus 2 Z power minus 1 cos omega naught plus Z power minus 2. Another signal, sin omega naught n multiplied by u of its transform can be shown equal to Z power minus 1 sin omega naught by 1 minus 2 Z power minus 1 cos omega naught plus Z power minus 2. With this, we come to the end of this session. Before closing the session, let us recollect the important topics we discussed, we touched in this session. A small historical background to Z transforms. It has been given, and then definition of the transforms. After touching ROC, we move to important properties of Z transforms, initial and final value theorems, and also a list of commonly used Z transform pairs. Hope this session is useful to you. We meet again in another session with a new topic soon.